In this video, guys, we're going to look at two more examples on second order differential equations, and just with slightly awkward particular integrals. Okay, so let's start with example 3. We've got dt by the x squared minus 5dy by the x plus 6y is equal to 6 e to the 2x. We're also given conditions so we can find the particular solution, not just the general solution. Let's start with the complementary function. And then that would give us m squared minus 5m plus 6, which factorizes. And we get two real roots. So for two real roots, distinct, it would be some e to the 2x's and some e to the 3x's. M equals 2, and m equals 3. Remember, we're just finding this coefficient for our exponential part of our solution. Okay. Doesn't matter which way around you do it. Sometimes people say, Josh, that should it be a or b e to the 2x's? So they're just constants that we're going to find. It doesn't matter. You could say a e to the 2x's, or you could say a e to the 3x's. I just normally go from in ascending order. So some e to the 2x's and some e to the 3x's. You can put them either way around. Okay. So now we need to look at the right hand side and think about our particular integral. I'm going to throw that pen away. We need to look at what's on the right hand side. And you would usually at this point think, all right, so for the particular integral, we need some e to the 2x's. But we've already got some e to the 2x's, so be very careful. And this is why you should always find the complementary function first. If you're just approaching this as like a full question in one go. If you find the complementary function, you can see that we've already got some e to the 2x's. So in this case, for the particular integral, I'm going to have to let y equal some x e to the 2x's. Okay, and once we've realised that, because we already have e to the 2x's for the particular integral, you then multiply that function by x e to the 2x's. You're then going to need to differentiate this twice, substitute it in, and let's see what we get. Okay, so if y is equal to c x e to the 2x, first derivative, again using the product rule, would be cx times 2 e to the 2x plus c e to the 2x. Okay, we're going to have to do the product rule again. You could, if you wanted to, there's a potential to rearrange this before you find the second derivative. Like you could take a factor e to the 2x out. So you might want to write it as 2c x plus c e to the 2x. You could even take the c out as well. That then, if you do it that way, means you just have to do the product rule once on these two functions multiplied together. It doesn't really matter as long as you're careful with your derivative. I'm going to use this form. So that would be 2 lots of 2c x plus c e to the 2x. Just from the if I differentiate e to the 2x, we multiply by 2 plus, and then I'll differentiate this one. So that would just leave me with 2c times by e to the 2x. Okay. Now we've got to substitute all this in to our second order differential equation. Could we tidy this second derivative up a little bit before I substitute in? You noticed, yeah, I'm actually going to write this second derivative as 4cx e to the 2x plus 2c plus 2c, so that'll be plus 4c e to the 2x. So that would become 4cx e to the 2x plus 4c e to the 2x minus 5 lots of the first derivative, which would be 2cx. I'm just going to expand it out actually so they're all like they look the same, and then c e to the 2x plus 6 cx e to the 2x. And all of that is equivalent to 6 e to the 2x's. So remember what happened on the first order, like you'll know if you've done it right at this point, because we're expecting this to just compare on the right hand side. We're just looking for e to the 2x terms. All these other terms, the x e to the 2x's, will have cancelled, hopefully. So let's see, how many have we got? 4 plus 6, there's 10 of them, minus 5 times 2, 10, yes, so they cancel, which is great. And then we are left with 4c minus 5c, so minus c e to the 2x equals 6 e to the 2x, and if we equate the e to the 2x terms, minus c equals 6, so c would equal minus 6. Okay, we're not quite done. These are quite long-winded questions, aren't they? So now we've got to figure out what our constants are using this information here. Okay, so my full general solution we should write down would be a e to the 2x plus b e to the 3x minus 6x e to the 2x. So there's my general solution. Should we use this information? So when x equals 0, y equals 3. E to the 0, don't forget, is 1. And if I sub x is 0 into this, that disappears. Okay. If to use my next piece of information, I'm going to need a bit more space, and I'm going to use the derivative. So I'll need to differentiate this. And I'll, again, be careful with the product rule for this. Okay, so if I differentiate this, divided by the x, would equal 2a e to the 2x plus 3b. E to the 3x minus, differentiate that, so that'd be 12x. E to the 2x minus 6, differentiate that, e to the 2x. And we know that when x equals 0, the derivative is equal to minus 2, so if we substitute that in, oops. Be careful, sub 0 into this, it'll disappear, and minus 6. Okay, so we get a nicer set of simultaneous equations. I'm going to use substitution. I know that b is equal to 3 minus a. So that would become 4. Um, 9, so then subtract 9 minus 5. 2a minus 3a minus a, so we get a equals 5, therefore b equals 3 minus a, so minus 2. Let me just check I've done that correct and we'll write the full solution. Yeah, so we'd get particular solution y equals 5 e to the 2x minus 2 e to the 3x minus 6x e to the 2x. Okay, one more example, guys, and then you can practice some. Okay, so slightly different structured example. Let's just read through it carefully and sort of pick out the key points. It says, it is given that the general solution to this differential equation, now if you notice this differential equation, dy by dx squared minus 2 dy by dx plus y is equal to 0, that is usually when we set our differential equation to when we find our complementary function. And then we look at the differential equation that we're being asked to solve and notice that actually it's the same, left hand side is the same, but we've got 60 to the x. So what this is telling us, the solution to this when it's equal to 0, that basically what they've done there in this question is they're just giving you your complementary function, they're saving you the trouble of having to solve a quadratic. It's very nice of them, but that's our complementary function to this differential equation. And now we need to find our general solution. So we just need to find our particular integral, don't we? And then we've got our general solution. Now if you notice, when you're finding your particular integral, natural instinct would be to let y equal some e to the x terms. But be very careful. We've already got, if you expanded this out, sometimes people miss this, because it's written in this form. I've seen people miss this before. If you expand that out, you've got some e to the x's. There's a constant times by e to the x, so it doesn't make any sense to use a constant times by e to the x. And you've also got a constant times by x e to the x. So you don't want to use x e to the x either. We've got some e to the x's, we've got some x e to the x's, so the next step up we multiply by x when we've already got that in our complementary function. To find the particular integral, the rule is you multiply that function by x and then you retry. So we're going to be using this. Once we realise we're using this, we can differentiate, and that would become cx squared. Differentiate e to the x, you get e to the x plus, differentiate this, 2cx e to the x. Again, you might want to take a factor out there, so you only have to do the product rule once. You can take the e to the x out. I'm just going to do the product rule again. Cx squared, differentiate this, e to the x plus 2c x e to the x. That's just from the product rule with this. We've got those two terms, and now we'll do the product rule with this, so that'll become plus 2c x e to the x just by differentiating that one. Now if we differentiate this one, that'll become plus 2c e to the x. Okay, let's substitute in. Could we tidy this up first? That'll be, yeah, there'll be 4 of those. So we've got c x squared e to the x plus 4 cx e to the x plus 2c e to the x minus 2 divided by the x, which would be c x squared e to the x plus 2c x e to the x plus y, which is that, and then that's equal to 6 e to the x. Do you understand why I said in the last video, like, it's really important that you guys actually practice this technique? Like, look how accurate and how thorough you've got to be in this. Like, you know, your brain needs to actually do this. If you don't sit down and spend time on this, you aren't going to be able to replicate it for yourselves. Okay, so please practice these questions carefully. Let's see, have I done that right? I hope so after saying that. So we've got cx squared, so there's 2 of those, minus 2 of them, yeah, they cancel. Remember, we're only expecting to get e to the x terms, aren't we? And what about the x e to the x's? 4cx minus 4cx, yeah, they cancel as well. Okay, so we have just got 2c e to the x equals 6 e to the x. I think clearly we can just see that c must equal 3. Okay, and we're done. All right, so find the general solution. It would be e to the x ax plus b plus 3 x squared e to the x. Alright guys, hopefully that was useful. Again, maybe rewatch some of those if you need a bit more practice. Check the booklet for the different types of complementary functions, particular in schools. Keep that with you for reference while you're practicing these questions. And then get stuck into those 2 exercises with lots of practice, and you will need to do it. Okay, so obviously you're going to work on that over the next couple of weeks, and then there's an assignment due in 2 weeks' time. Hopefully the video was useful, guys. Let us know if you need any help. Thanks for watching.